So in chapter 8.2, we're going to look at confidence intervals for an unknown population standard deviation. In this case, sigma is not known. So we're looking at our first problem. It's problem 22 on page 375. In 2012, the General Social Survey asked 1,972 adults how many years of education they had. The sample mean was 13.37 years, with a sample standard deviation of 3.13 years. The first question is construct a 98% confidence interval for the mean years of education for adults in 2012. So if we use the calculator, we again hit the stats key, and we get the first screen for the stats key. We move over to test, and we pick option 8, which is the t-interval. Then from the t-interval, we pick the stats option, primarily because we don't have data. We enter in what x bar is. We enter in the sx. We enter in what n is, and we put in our confidence level, and we hit calculate, and we end up with the t-interval, which tells us that the mean years of education for adults in 2012 was 13.21 years to 13.53 years. So if we had to do this by hand, again, our estimate, right, it's going to be our confidence interval is equal to x bar plus or minus the margin of error. That's the point estimate plus or minus the margin of error. But x bar isn't going to change. Our x bar in this particular case, right, is 13.37. So that doesn't change. However, our margin of error does change, because here the margin of error is a t-value with degrees of freedom n minus 1 divided by sx, because we don't have sigma, divided by the square root of n. So in this case, we have to find a t-value, but because our size is so large, when we go to the table, we see that we go up to 200, and after 200, it gets very, very hard to find a t-value for a degrees of freedom of 1971. So in this case, we just use the z-value, which is 2.326, and now we multiply it by 3.13 divided by the square root of 1972. So once we have the margin of error, right, we then can get a lower bound and an upper bound from our point estimate. And in this particular case, we do 2.326 times 3.13 divided by the square root of 1972. And we get this to be 0.1639 about, right? And so our confidence interval is going to be CI is going to be 13.37 plus or minus 0.1639, and essentially we end up with this result here when we do the calculations for a lower and upper bound. So Part B says the data collected in an earlier study suggested that the mean educational years attained by adults in 2000 was 13.26 years. Is it reasonable to assume that the mean number of educational years attained has remained the same? And the answer is yes, because 13.26 lies between the lower bound and upper bound of the confidence interval, which is 13.21 and 13.53. So because it lies between there, we can assume that the mean number of educational years have remained approximately the same. In the second problem, we're looking at some data. This is problem 29 on page 375. The following are the weights in pounds of 12 2-month-old baby girls. And then the question is, can we assume normality from the population? So we end up drawing a box plot. And here's our box plot. We don't see any outliers, so we can assume somewhat normal distribution. So our first step is to construct a 98% confidence interval for the mean weight of 2-month-old baby girls. Well, in this particular case, we know when we put this data into the calculator, we will find that X bar from this data set is 11.4 approximately. So from the data set, we get our point estimate. Now, we also get SX, because we don't have the population standard deviation. We find that in this particular case, approximately the standard deviation is 1.8. Now, we want to find a 98% confidence interval. So in this particular case, we have to find a margin of error. Our margin of error in this case, because we don't have sigma, we have to calculate a t margin of error, which is Sx divided by the square root of n. Right? Do we know what n is? Yes. N is equal to 12. Right? So our degrees of freedom in this case is n minus 1, which is equal to 11. Right? And so now we go to table A3, and at the bottom we see 98%, and we go up that column until we hit 11, and we see that the t-value, right, that we're going to use is equal to 2.718. So that's the t-value we're going to use for our confidence interval. So we finish up calculating our margin of error, which is 2.718 times the ratio of our standard error, which is 1.8, divided by the square root of 12. And when we do this calculation, we get 2.718 times 1.8 divided by the square root of 12. And we get this to be 1.41. So now we have a lower bound of our confidence interval, which is going to be 11.4 minus 1.41, right? And so we get about 9.99, right? And for our upper bound, we get 11.4 plus 1.41, which is approximately equal to 12.81, right? And so if we look at these two values in comparison to what we got on our calculator, we're pretty accurate, right? So again, when we use the calculator, we hit the stats key, we come over to test, we choose the t-interval, we pick the data, because we have data, we check the list that we've got the data in, and we also make sure that the C level is 0.98. We hit calculate, and then we get the t-interval lower and upper bounds. Our last question asks, if the mean weight of baby boys is 11.5 pounds, is it reasonable to assume that the average weight of a 2-month-old babies are not gender dependent? And in fact, they're not, because if we look at 11.5, it's in between the lower and the upper bound. So the answer is yes, not gender dependent. At this stage of the game, obviously, as the kids get older, of course, that would change. Weight changes based on the gender. That concludes our problems in chapter 8.2.